So I'm really excited to be here, and thank you for organizing this workshop. To some extent, I think over the years, interactive systems is something that I've been working on again and again. So it's really great to see a workshop in that space finally. So I was really conflicted about what to talk about here, and I also had it was kind of like a near miss of getting this talk done. A few days ago, I was just about to email the organizers and cancel the talk as I broke my wrist, and most of the slides, not surprisingly, weren't ready. Luckily for me, that my students jumped in, and Nori and Elaine did much of the work to make this happen. And I was saying there's a lot of work following Dorsey's talk on robotics. I'm a bit conflicted, and sorry I'm not talking about our robot and language work, but I'm almost a person of like limited attention span, and I was more excited about talking about the most recent stuff. So I want to talk today about our recent work on continual learning through collaborative interaction with users, and specifically with focus on generation. I know these setups is even after a year and a half in this hell, this is a pretty awkward. I usually find it the most helpful for everyone if it's more interactive. So feel free to barge in. I'll do my best to monitor the chat, and I'm more than happy to, I'm actually would love to take questions throughout. Okay, so the talk will be divided into three major parts. In the first part, I'll kind of like in a very abstract way describe the types of scenarios I'm interested in and that are the focus today. In the second part, I'll describe serial bar, which is an instantiation of this scenario in an instructional game. And finally, for the bulk of the talk today, I'll focus on some very recent work on instruction generation learning, specifically with focus on continual learning in this kind of collaborative scenarios. Okay, so the kind of scenarios that we're interested in have at least two agents, a human user and a system, and these are collaborative scenarios. So something that is really important we're going to emphasize is that both of these agents act and change the world. And they coordinate using natural language. So just to kind of like to make it a bit more grounded, you can think of the system as a robot in a physical environment, or working together alongside a human, or a virtual agent in a structured software environment. So maybe you are kind of like building this crazy spreadsheet together with the virtual assistant, and you're kind of like delegating each other tasks and coordinating using natural language. So as you can already understand from this, as far as the language problem, this kind of scenarios offers a very broad perspective of language. We have problems of language understanding. So for example, if you give instructions to the system, you would like to follow them. There are problems of generation. The systems can potentially ask for questions or clarifications, or it can give you instructions by delegating tasks to you because you're also operating in the world. So depending on the setup, we are kind of like looking at the full-fledged dialogue problem. Another very important aspect of this kind of scenarios that arises from the collaboration is dynamic delegation. So users can kind of like dynamically delegate tasks, and they can adapt and see how the system is responding and decide to do certain things on their own and certain things that are better delegated to the system. So you can ask the system to do something, see that it's maybe not really understanding you, or maybe it's having a hard time doing that. So you say, okay, because I can act in the world, not everything is lost. I'll just do it myself, and I'll delegate other tasks to the system. And this is really going to be something very important when you talk about problems like continual learning and adaptation. So as far as learning, this kind of scenarios where the user is sitting there in the system and working with it together are great facilitators for learning on the fly from interactions. And there are numerous types of learning signals that you can encounter. Some of the clearest ones are explicit feedback, for example. You can give the system an instruction, and then as you observe it executing it, you can give it like, even the simplest kind of like binary signal, positive and negative signal, if it's doing good or bad. Another type of signal that exists in this kind of system is observational signal. So for example, if the system tells you to do something and then observes you and sees that you're doing something completely different, it can infer that maybe it didn't express its intents correctly, and it should maybe adjust how it's generated the instructions. And of course, there are many other signals in this kind of rich interaction. So Serial Bar is a collaborative game that instantiates this kind of interaction scenario with a sequential natural language instruction. So in Serial Bar, there are two agents that collaborate in an environment. They both act in the world, so they have this like very important part of collaboration. And there is a unidirectional natural language instruction channel. So one of the agents is a follower and another is a leader. And the natural language only goes from the leader to the follower in the form of instruction. So this scenario is relatively expressive. It allows us to study a very interesting learning algorithm, but it's also scoped because it doesn't require addressing the full dialogue system. And this, in a way, allows us to focus on maybe more complex or weaker learning signals. Okay, so this is the Serial Bar environment. Each of these, this kind of environment is generated randomly for every game. So every game has a new environment. This environment includes passable terrains, impassable terrains, different types of landmarks, and a lot of cards that are spread around this environment and have like different colors and patterns and numbers on them. In this environment, we have two agents. We have a leader. This is this colorful figure on the left. And we have a follower, the monochromatic figure here on the right and on the left. And the two agents together, they play a game that, if you're familiar with, is very similar to the card game set, but takes place in a spatial environment. So they go around the environment and they collect valid sets of 3 cards, where a valid set has a unique color, shape, and count. And each time they complete a set, they get a point. So just for an example, this is an example of a valid set of cards because each of the color, shape, and count are unique, whereas this set is invalid because the count 3 appears twice. Okay, so the two agents, they move around the environment and they take turns, and in each turn they have limited number of steps. So they move around the board, they select cards, and when a valid set of cards is selected, the cards disappear and new ones randomly appear in the environment, and the agents get more turns when completing the set. So the better you do, the more turns you will get, and you will have a chance to even score higher and higher in the game. So there is like this kind of like, the richer gets rich kind of scheme happening here. So let's look at a very kind of like short example to see dynamic. So here, for example, this is our leader and here is our follower. And the leader will start by, in their turn, taking this yellow plus. The follower turns around, grabs this like 3 red bars, and then the leader in their turn will complete the set using these 2 pink stars, and the cards disappear. Okay, the agents, they select the cards together. So the set is something they create together, and the leader instructs the follower using natural language, and the goal of the follower is to just follow instructions, to do what the leader says. They can execute multiple instructions per turn or one instruction across multiple turns. And we do several things to incentivize and kind of like bake collaboration into this setup. So first of all, there is an observability gap between the two agents. The leader sees the complete board while the follower only sees what is ahead of them. So they really have to follow what the leader tells them to do. Otherwise, they are doing something suboptimal and they are risking sabotaging the sets the leader is planning. On the other hand, the leader shouldn't really go alone because the follower has many more steps per turn. So they are like the workhorse of the game. And so usually if the leader wants to kind of like really collect as many sets as possible, they really need to use the follower efficiently. Okay, so let's go back to our example and see how it looks from a different perspective. So at the top is the leader perspective. So you see the overhead view of the board. They give an instruction, grab the free red stripes behind you. And here at the bottom is the first person view of the follower. They have occlusions. They don't see what is behind them. They just see what's in front of them. In this case, they don't even see the free red bars that the leader asks them to collect. So the game starts with the follower turn, leader turn, where they collect the yellow plus. Then the follower turns around following the instruction and collects the free red stripes. And then the leader completes the set and the cards disappear. So the serial bar scenario emphasizes four important aspects in its design. First of all, it's a spatial reasoning. So the interaction happens in a dynamic 3D environment that keeps changing as cards keep disappear and appear. It's a collaborative interaction, and working together is really critical for success here. The way the initial number of turns and the number of steps is set means that if they don't collaborate, they're just not really going to get very far. It has sequential instruction following. So, and this includes dependencies between instructions, planning ahead, changing goal between instructions, and instructions that include multiple sub-goals. For example, picking up, selecting or deselecting multiple cards. And finally, the interaction is really an important component here. Both agents are in the interaction. So it's not just you give instructions and you go make yourself coffee. You're sitting there constantly, which gives you this opportunity for both of them to continuously adapt and modify their strategy and become better at it. Okay, so let's look at a slightly more interesting example. So this is from a data set we collected with human games. You can think about it as creating a Wizard of Oz scenario. And this is a pretty good interaction. We have the leader here and the follower here. The leader starts by giving the instruction, turn left twice and head straight towards the doghouse and look for 2 green circles to pick up. So basically, it wants the follower to pick up this. The follower is facing in this direction, and this is what they see. This is a first-person view here at the bottom left. So as I'll play this video, it starts with the follower kind of like turning a bit too much, going in the other direction, but they're going to correct themselves. In the meantime, the leader goes and collects this card, so they're starting building a set. The follower collects the card. The leader gets their turn. The leader tries to get in their turn to collect the third card and to complete the set, but they don't have enough steps for it. So what's going to happen now is the follower is going to get their turn, but the leader doesn't want to waste the follower turn, just having them wait for them to collect this card. So what they're going to do is they're going to plan ahead, and they're going to ask the follower to turn left and head towards this yellow hearts card here, but don't pick it up for now, and because you have to get the leader has to get the card first, because otherwise it will sabotage the current set. So whoops, sorry. Okay, we'll have to go through that again. And we were here. So the follower will position themselves but not collect this card. The leader will complete the set, and then in the position for the next card, and then they give the next instruction. The next instruction, they're really taking it, they say, okay, now pick up the card I told you because we are in the next set. And I'm going to use the fact that you have so many steps, and I'm going to send you to the other side of the board to collect cards. So go past these sticky bushes on the left end and get the free green star, and where there is a free green star. I'm not telling you to explicitly collect them, but there is some kind of like implied expectations here. So the follower does that. They position themselves next to the card, and then the leader tells them, okay, after you get it, so now I'm implying that you should get it, although I'm not telling you that exactly. After you get it, pick up some other cards and let's go, and we're going to continue and do another set. So you see this a lot of planning, multiple sets, kind of like crossing between instructions, and a lot of like very interesting dynamics happening between the players as they are optimizing to use their turns in the best way to increase their score. Now, there are many possible tasks that you can study within a serial bar, but the two core ones is a language understanding, so instruction following, so mapping leader instructions, the history of the interaction, and the first person observation of the follower to follow actions. And the other one is generating leader instructions. So given the world state as the leader sees it and the history of the interaction, generate an instruction for the follower to follow. When we introduced serial bar in a previous paper, we proposed an approach to solve the first task using this Wizard of Oz supervised data that we collected, the human games. And what I'm going to talk about at the rest of the talk today is an approach for generation learning. So addressing the second task of generating instructions. And we're going to do it with a focus on continual learning. Okay, so what does it mean to generate instruction in serial bar? So the input that you're getting is kind of like the world state from the view of the leader. And the output is an instruction describing how the follower should move in the world and select cards. So for example, here, this is our follower and the leader wants it to go around past the lake and pick up this like blue circles here. So turn right, go straight past the lake and collect the free blue circle card. So there is a clear intent communication, which really distinguishes the goals of this system from chit chat systems or systems that are optimizing for maximizing user engagement over time. It's really about task completion. And the first thing we need to do is we need to decide about what the cards the follower to select and what path we want them to take. So for that, we are solving it with a very simple deterministic planner that kind of like finds that optimizes according to the position of the two agents to which set to select and which card each of the agents should select. So this is a deterministic planner, and it's to give us a sequence of follower poses. So poses the follower should take as it moves along a trajectory to pick specific cards. So this leaves us to the crux of the problem that we're interested in. This is the language generation problem. So the problem is that given a world state, which I'm going to denote kind of like with this globe here, and a plan, which I'm going to use this map icon for it. We want to generate an instruction that the leader gives to the follower. This instruction must use landmarks because the follower has partial observability. It must be from the follower perspective, not from what the leader sees. And it must exactly specify what cards to select or deselect. So this you can think about is like the goals, the sub goals of an instruction. And there can be 0 if the instruction doesn't require any card collection, or there can be multiple of them. Okay, and the main question that underlies the study that I'm describing today is can we learn to generate instructions by observing human users executing them. So let's see what it means. So assuming that we have a language proficient and a collaborative instruction follower, a good instruction relays the system intent well. And this will allow the follower to execute it as intended, right? A bad instruction is either inscrutable, so you don't get anything out of it, or results in an unintended behavior. So the response does not align with the original system intent. For us, the system intent is this plan that the planner gives us. So if we compare what the follower did to the original intent, this can give us an indication of the effectiveness of our generation, of our communication channel. Okay? And there is a very nice connection here to cognitive science and psychology studies that indicate that this kind of signal influences human language learning to various degrees. For example, for morphology learning, it's actually, in some languages at least, it's known to be relatively ineffective and not of much contribution. However, for adaptation and lexical choice, it seems to be more influential, and Krauss et al. As early as 1966 showed that this very similar signal that they call confirmation feedback influences conversion formation in a very primitive form of a reference game. And later on, this was reaffirmed in more contemporary studies of reference games, in several studies from between 1966 and more recently in 2020 by Hawkins et al. So loosely speaking, this kind of connection to cognitive psychology indicates that there is a potential in this learning signal, but also, and this is maybe even at least as important, that the humans have the expectation that this kind of signal manifests in interactions. So they expect to it. It's natural to them. So it will be kind of like, you know, a good opportunity for us to, as a machine learning researchers, to use it. There is an important caveat here, and I think kind of like important to put it on everything that draws connections to cognitive psychology. This is a very weak relation to human reasoning and learning, and it starts and ends here. Everything that I'm going to show from now on, we don't really have a good understanding of how it relates to human reasoning. It's a very interesting direction to study, but this is not something we have done. Now, in generation learning, this kind of signal, at least to the best of our understanding, is extremely understudied. We are not familiar with any study that shows effective use of it, especially like with experiments in the wild. And it's different from some of the kind of like common signals or even less common that we see used for generation learning. The system doesn't solicit written instructions, so it's not similar to how we annotate instructions or language generation in general. And it's not similar to what we do with active learning, where we choose examples to label and go to oracles and ask them to, in this case, write the instruction. We are just observing executions, and the whole instruction writing is happening generated by the system. The signal is also distinct from explicit feedback, which meaning that the user tells you if your output is good or bad, because this requires knowing the system intent. In our case, or for example, in machine translation, to have some idea of the translation. In summarization, where it's also been used, it requires some idea of like what would be a good summarization, and also some idea about what document you're starting for. So the important thing here, this is really a natural byproduct of the interaction. And this is the key to really facilitating continual learning through the interaction with users with a very limited or even no overhead. Okay, so before I describe the kind of like building blocks and the learning algorithm, I want to put everything in perspective. So show you an overview of the entire system. The details here don't matter because we're going to go back to this slide after we know what goes in each of these boxes. So we start by initializing our system with a minimal amount of supervised data just to get it to kickstart the learning. And we also initialize our decoder, the generation model, with a GPT-2 weights to give it some kind of an idea of a language of general language model knowledge. And then we have a generation model and we start deploying it, and we are doing it in rounds. In each round, we are interacting with users, and during this interaction, we are going to sample instructions given the current state of the interaction and everything from our generation model. From these interactions, we are going to observe what the users are doing, and we're going to construct the training data, which we aggregate over time. So the data set constantly grows as we interact more with the users. And then at the end of each of these rounds, we do offline contextual bandit training to create a new generation model, which we deploy for the next round. Okay? Okay, so how does this work in serial bar? So the human users are our followers, and the system is the leader. Users only see the natural language. They don't see what the system intends for them to do. There's no any sort of visualization of that. And the collaborative goals that are baked into serial bar, they are what is responsible for aligning the human follower incentives with successful intent communication. So the humans are really incentivized to understand what the system tells them and kind of like and help and work together with the system. So we have this very collaborative, language proficient follower. The language channel is unidirectional, which is a slight limitation for us because we would like to have some kind of feedback for like at least blatant errors. So if the user wants to tell us this doesn't make any sense, or I have no idea what you said. So what we do is we add feedback questions, like 2 binary feedback questions about perceived correctness and grammaticality after each instructions to catch these really bad cases. Although later on we experiment without these feedback questions as well, and you can see kind of like how the influence, it's a bit more nuanced than we initially expected even. Okay, so how does it look from the user perspective? So I'm going to take you through 2 examples here. Basically 2 instructions that the follower is getting from the system, and the whole process that they are going, how the interaction looks on their side. So this is the perspective. This is the entire interface actually. You see that they see the environment. Currently, it's the leader turn, so everything is disabled here. And the leader gave them a new instruction: turn right and go straight past the lake and collect the free blue circle card. This is actually instruction generated by our system following the learning. So the leader gives them this instruction, and then they are getting their turn. You see everything became green, so now they can move in the environment, and they start executing it. So they go straight, they pass this lake that they're seeing here, and then they see this like free blue circle card. They go and collect it. In the meantime, they ran out of steps, so it's the leader turn now, and it will go back to them. Control will come back to the follower in a second. They collect the card, and they indicate that they finished the instruction and they want to get the next one. And then they get a question: did you follow all parts of the leader's command and find everything correct? So this is a perceived correctness version. What we are showing them is what they did, not the original intent. So it's just a visualization to remind them what they have done. And we ask them, do you think this is correct given what you were instructed to do? So in this case, they're going to say yes. And then we ask them grammaticality. Is it grammatical and well written? This is grammatical, so great. So then the leader gets their turn and they give them another instruction. In this case, the new instruction is turn left, grab the black star, and then the 2 green squares, then the green squares. You can already see that something here doesn't make sense, especially if you are really proficient in the rules of set. So they're going to try to execute it. They're going to turn left, and they're going to look for this here. You can see that they're seeing this like black star. They're going to grab that. Once they're there, they also see the green square, so they're going to also run to that and grab that. And then they will finish the command to get the next one. And what they're asked is this: do you perceive it as correct? They're going to say no, because they didn't really complete everything, but it is grammatical. Okay, and the interaction continues. They get another instruction. This continues until they actually run out of turns, and it can be pretty long, because especially as the system gets better and gives better instructions to the follower. Okay, if there are any questions so far, please, I'm happy to answer either in the chat or just unmute yourself and jump in. Okay, so this kind of interaction gives us data that looks like this. For every example, we get the world state, the world start state when the instruction was given. We get the system plan, what was the underlying intent that wasn't visible to the user. We get a generated instruction. This is the instruction that we sampled from whatever was the model at that time. We can record the user execution, and we also have the responses to the perceived correctness and grammaticality binary questions. Now, something that is important here is that the system plan and the user execution, they actually follow the exact same representation. They are both sequences of observed poses, and this is going to be useful because we are going to kind of like treat them interchangeably and compare them while we are processing this data. Okay, so using this data, we compute a reward. The reward to do this, we compare the system plan to the user's execution, and if they diverge, we know that the instruction is not a good representation of the plan, because otherwise the user they wouldn't have diverged, or diversion would have been very small. So the system intent was not relayed well by the instruction, but the execution can still align with the instruction, especially if the user perceives their execution as correct, even if unrelated to the underlying system intent. So we have 3 heuristics to compute reward and construct training data from this kind of interaction data. If the feedback is incorrect or ungrammatical, we know we have a bad instruction. So what we're doing is we are pairing the system, the world state and the plan. These are like the model inputs with the generated instruction with a reward of -1. So this is a bad example, a negative example. If the instruction is correct and grammatical, what we can say is that the execution reflects the instruction meaning. Not necessarily the plan, but the execution reflects the instruction meaning. So we can construct a positive example by using the world state, the execution, as both of those as inputs to the model, and we can do this because the execution is also just a sequence of poses, and with an output as our instruction, and with a reward of +1, so a positive example. Now, if in addition, the plan and the execution are equivalent, then we can say that the instruction actually accurately communicates the plan, and we can construct a positive example using the world state, the plan, both of those as inputs as model inputs, and as outputs the generated instruction with a reward of +1. Okay, so this kind of training data that it gives us, it gives us these tuples of model input of a state pose sequence, either from the plan or the execution, generated instructions that we sample during learning, and rewards that are either +1 or -1. And this creates a very nice contextual bandit scenario. Now, bandits are really advantageous for this kind of learning, where examples are really expensive. Bandits are relatively, when I say relatively compared to something like reinforcement learning, are very data efficient. So how is this a bandit scenario? So our context are the model inputs, what we conditioned on when we create the instructions. These are the state and the pose sequences. And the bandit decision is the instruction. Now, even though that our decoder might have a sequential decision process that generates the instruction, as far as the learner is concerned, this is a single action process. There is no sequence. And this is because the reward can only be computed on the complete decision. We can only ask for execution once we have the complete instruction, and anything that we try to do as far as like create assignment there is pure guesses, unless we employ more complicated mechanisms. Now, the advantage of treating this as a contextual bandit scenario is that it reduces the problem, or at least brings it very close to a supervised learning problem. And this is really nice because we know how to do supervised learning. We know how to get optimizers to behave well. We know how to we know it works really well. It's relatively data efficient. We want to be in that scenario. It's not really supervised learning for two important differences. One of them is that the data comes from interaction with users. So but it's very nice because we were able to take data from interaction and actually plug it into this, put it in this box where we know how to deal with things relatively well in NLP and in general in machine learning at this point. Okay, so our training objective is maximizing the reward, and let me just for these two slides add a bit of notation. So we have a state S, pose sequence row, instruction X, and a reward of Y. And the gradient of this, and you can already see how very similar it is to supervised learning, is just the reward multiplied with the differentiation of the probability of the observed instruction. Okay. So you can see that if we take positive examples with a +1, this Y just is kind of like disappears, and we get just a supervised gradient, which is fantastic. There is a big problem here, though. It's kind of like latent time surface is what happens with negative examples. So with negative examples, intuitively, what we try to do with them is we try to kind of like drive the probability of these instructions to 0. But as we push a probability to 0, the log probability will go to -infinity. And this is going to explode this loss. Negative examples will take over the loss term and will derail learning completely. So we don't want that. And we do something relatively simple to address this. We borrow a technique that is very common in contextual bandit called inverse propensity scoring. It's usually used for debiasing examples, and we are using it slightly differently, but in a very similar way. We are using it to basically overcome this issue of the loss exploding because of the negative examples. So what we're doing is we add to the objective term this coefficient curly L, and this coefficient is computed using the label. For positive example, it's just 1. It doesn't do anything. For negative examples, it's going to be the IPS coefficient, the inverse propensity score, which is the ratio between the current probability of the instruction under the current parameters whenever you are doing learning over the original probability and for when we sample this instruction. So what's this going to do is, like, as we drive the probability of the instruction to 0, the importance of that example for the loss is also going to be driven down to 0. So it's going to basically be insignificant as the probability becomes really small. Okay, so let's put it all together. So, okay, so where were we? We initialize with supervised data. So we use a very small amount of supervised data for initialization just to get us off the ground running. And we also use GPT to weights. We get our model, and then we start running these rounds. We sample from our model instructions, given that whatever state we are in during the interaction. We interact with the user. We collect this data, these tuples, and we, using the heuristics, we construct training data from them. This training data we aggregate to a data set that becomes larger and larger over rounds. And then we do offline contextual bandit training from scratch every round in order to get a new generation model. Then we deploy this model and we repeat this process. Okay, so the model that we are using is an encoder-decoder architecture. It's pretty simple model. There is a spatial encoding of the environment and the system plans. This gives us a sequence of vectors. And then we have a GPT-2 transformer decoder, which is like a shave. We take the GPT-2 and we shaved a bunch of layers just to get it more compact. We extend it to condition on the encoder output using a technique called pseudo self-attention. Okay, so for our experiments, we initialize the model using 360 without the false interactions. We evaluate using task completion and similarity of execution to the system plan using Earth mover distance. So this is task completion of the humans trying to accomplish the instruction that we communicated to them, and the Earth mover distance between their trajectory and the plan. We generally found n-gram similarity measures and even like more complex measures like BERT score to be largely useless for measuring quality in this task. And this means that we don't really have a good automatic stopping criteria. So what we do is really silly and suboptimal. We just pick what we think is a reasonable fixed number of epochs, and between each round when we retrain, we just train for this fixed number of epochs and take the model at the end. Okay, we do a number of experiments. Each of these experiments is relatively complex, relatively expensive. It's all done with live users. The first one is a long-term study where we run our system for 14 rounds to observe learning trends and interaction trends. And what I'm showing here are task completion rate and Earth mover distance. We want task completion rate to go up, Earth mover distance to go down. I'm breaking performance here. So the blue line, the bold blue line, is overall task completion rate and Earth mover distance. And I'm also breaking it according to categories, depending on how many cards the underlying system plan intended for wanted the user to select during the execution. So 0 cards are instructions like wait, don't do anything, I'm doing something else, or something like that, or hold still. While the other ones are 1 card, 2 cards, and 3 cards. And you can see that in general, over rounds, the model continually improves in generating instructions that relate to intent. Multi-goal, this is across both task completion, and also we get much stronger similarity between the trajectories, the trajectory and the underlying plan as the system progresses. This is and what we see, and when we break it into categories, and we see that multi-goal instruction actually take much longer to pick up. So very fast, we actually start pretty good on zero card, and even one card, and we pick up very fast. With two cards, it takes us a bit longer to pick up, but we get really good performance. And with three cards, it takes us even longer, and then we start picking up at around round 8. Another thing to notice here is this, like after about round 8, we have a small drop in performance on one card instructions, and I'm going to go back to that a bit later. Okay, we also see that the system just performs better. The user's perceived correctness increases over time. Again, we can break it according to categories, and you can see similar trends. With two cards and three cards, it takes longer until it happens. The game score also increases over time. So the game score starts from 4.5, so at the beginning, and goes all the way to 2.4 at the end. So really drastic improvements. We also analyze the language, and this is a thing where we saw some kind of like some surprising results that how language changes over the system's lifetime. In general, language becomes simpler, and this is potentially happens because the language is more attuned to the task. So we see the vocabulary size decreases over time. That's the blue line, and the mean instruction length also decreases over time. And a lot of this is because the system drops words. It really doesn't know how to use well, or it often tends to, at the beginning, it has this like suffixes that don't make any sense at the end. It drops those as well. So this is good, but it's also slightly overcompensating, and it has a harder time describing more descriptive paths later on. And this is the reason why we saw this drop, the sudden drop in the performance for one card instructions at the beginning, at around the middle of its lifetime, around round 8. As far as syntax, things are a bit more complex. We see when we look at dependency structures, we see that the max depth decreases, so simplification, but the branching factor significantly increases, while the max width kind of like stays the same. So what kind of data that we are getting during the lifetime? So this is also something that evolves over time. So we can look at like how many negative and positive examples we are getting. So in general, later on during the lifetime interaction, we get more data per round because the interactions are longer. The system is much better performant. If they get more points, they get more turns. They can interact for longer with the user. So in general, we see more instructions. But even more interesting is like in general, the number of negative instructions per round decreases throughout the system's lifetime, but the overall number increases, and the number of positive instructions increases. And when we break this trend according to the categories of 0 card, 1 card, 2 card, and 3 card, you can really see how this distribution of examples explains the kind of like the bootstrapping process that we saw. So 0 card, we start very good, and negative examples almost disappear. For 1 card, negative dominate in the beginning, but very quickly, positive examples overtake them. With 2 cards, we start really bad. Almost no example is right at the beginning, but we very quickly learn, and at the end, the positive examples really dominate. With 3 cards, which are much more rare in our system because they require kind of like having cards that are located one next to another, then when the beginning, for quite a while, we don't see any positive examples. That's why learning takes such a long time to pick up. But once we pick up, we barely see any negative examples after a while, and only positive ones. Okay, the next study we did is we compared our system to different variants of learning. So I think I'll go through that for many slides really fast. So I'll be happy to go back to them if there are questions. We compare our full setup. POS only uses positive examples, so no negative examples. TC only ignores the feedback questions completely. And fine-tuning uses fine-tuning instead of retraining, which was a bit harder to get it to work because it requires additional decisions about hyperparameters and learning algorithms. In general, we see that the system is pretty robust to the different decisions. We see that using only positive examples slow down learning. The feedback questions are not necessary for learning, but they do give a system that has higher perceived correctness rate. Fine-tuning is actually potentially better at keeping a more diverse vocabulary, although we do think that this result requires a further study. And without negative examples, the vocabulary and the instruction length decay much faster. So negative examples are pretty important there. We also had another experiment we compared to supervised learning. Surprisingly, despite the fact that we don't require any written instructions, for supervised learning, overall our data performs much better compared to similar amount of supervised learning. I will skip the error analysis and I will just thank the students who did the work. So serial bar is the work of Elaine Soar together with the game designed by Claudia Yan. The generation work that I described is the work of Nori in collaboration with Elaine. I think I'm over time, but I'm very happy to stay as much as possible to answer any questions. Thank you. So this is a great question. So I don't think we qualitatively analyzed for that. So I don't really have an answer. There is nothing that prevents this from happening conceptually, but I don't know if it's happened. What we did notice as the instructions get shorter, what the system tends to do, it tends to really give up on more descriptive language. And the drop that we see in performance for one card instruction is because of that, because the instructions that it starts messing, the plans that it has a harder time describing are plans that require a more, I don't know, flowery language, if you would like, more descriptive language with like a more complex use of spatial relations. So this is what I know, but we didn't measure for the reduction in other semantic phenomena. This is a great question. Should have done that. So these will be separate examples in the training data. So these classes are not additive. They're just going to be. That's actually a great point. I think this doesn't come with the visualization. So basically, we are potentially creating up to 2 examples out of each interaction. So if it's correct and grammatical, then we will create the middle example. We create this example. And if it's also the plan is equivalent to execution, then we'll create an additional example. So there's actually this thing where there might be more training examples generated from an interaction than there are instructions. Yeah, we just made the system move very fast. It's more about you want to pay workers. You don't want them to just stare at the computer and tell them somewhere in the background the agent is moving. Give it its time.
Yeah.
So I think that so something to think about in natural language because of how natural language is structured. We are in practice we are generating 1 token at a time, right? Mm-hmm. And if you think about it, reinforcement learning, with some kind of like what is it, like a gamma there, I think, some kind of a decay parameter, discounting parameter for the reward, then that means that you will have the reward will be more significant, more impactful on the final tokens than on the first token. If your discount factor is not 1, or not 0. I always mix them up. But there is no reason for that, right? You don't know where your error is. So there could potentially be more complex mechanisms that are able to do it, like reward learning or something like that, but it's not really necessary. The nice thing the nice thing about contextual bandit, and there is a lot of theoretical work about it, it's actually just behaves better in both in theory and in practice. And We have seen this repeatedly in our work, where I remember the first time we used contextual bandit, my students was, it took him 2 months to convince me he doesn't have a bug in his code, because I told him, oh, DeepMind can get reinforcement learning to work. You must have a bug in your code. And no, he didn't have a bug in his code. He was just, it all builds on top of like this sample complexities that are very hard to satisfy. And it's very finicky. Now, it doesn't mean it's bad. It's just, pros and cons. Yeah, so I mean, it's definitely a challenging signal, and there is a very big problem of crate assignment. But in practice, it seems to work fairly well and relatively data efficient. You could, I think, an interesting direction is kind of like maybe learn some kind of a function that does the crate assignment in a slightly more nuanced way, but that will require extra machinery. So I think it's an excellent question to ask and it will probably further reduce the sample complexity and might take care of some of the issues that we see where it simplifies the language. I don't know. This is more speculative. I mean, I think maybe what you are indicating to is some kind of like an inverse RL, where you can use the bandit feedback to learn a more nuanced reward function, and then do kind of like basically RL, which is with the learned reward function. Yeah, I mean, I think it's an interesting direction. There is definitely a connection here to inverse RL.